So section 4 of chapter 7 deals with the physical properties of liquids. So we looked at the physical properties of solids. Now we can look at the other condensed phase, that is liquids. And there are some similarities, but there are also some differences. So viscosity is a physical property of a liquid, and viscosity resistance to flow. So if you have molasses, you might say it's flowing as slow as molasses. Molasses has high viscosity. Okay, it has a lot of resistance to flow. Okay, and different liquids have different resistance to flow. And as it turns out, the stronger the intermolecular forces, the more viscosity there is in a liquid. Okay, so all of this stuff is connected to intermolecular forces that we talked about in the last chapter. And so, again, viscosity, measuring liquids' resistance to flow, stronger intermolecular forces usually mean higher viscosity, less flow. Surface tension, something that you've also probably experienced. Have you ever overfilled a glass of water where water is looking to, it seems to be higher than the actual top of the glass? That is because of surface tension. Or if you've ever floated a needle on water, or you've seen insects that are kind of floating on water, that has to do with surface tension. Okay, and it's also another intermolecular force that increases it's not an intermolecular force, it's a physical property that increases in strength when intermolecular forces increase in strength. Okay, and so surface tension, viscosity, those are the two major properties of liquids. Now, liquids also have a property known as vapor pressure. Okay, and substances, if something has a high vapor pressure at room temperature, we say that's volatile. So if you're ever at the gas station and you smell gasoline, that's because gasoline has relatively weak intermolecular forces, and so those particles are not held together really strongly, and therefore they come apart and they go into the gas phase more easily, and that's why you can smell them. Okay, substances that have low vapor pressure we use the term non-volatile. Okay, so if we look at this, if we think of this as the kinetic energy, or the amount of energy required for a molecule to pop into the gas phase, at low temperature, most molecules are going to be in the liquid phase. They don't have enough energy, but a small fraction has enough energy. But if we increase the temperature, you can see a larger proportion of the molecules will have enough energy to hop out of the liquid phase into the gas phase. And so they have more vapor pressure. And so the way that this works is, if we've got a substance, or if we've got a liquid and we've got a gas above it, but there's essentially no gas here, what happens is initially some vapor is going to jump into the gas phase. And that's this first step. In the next step, what also starts to happen is some of those particles kind of slow down and they go back into the liquid phase. Okay, and but the amount that go into the gas phase stays the same, and eventually those two things equal each other out. And when they equal each other out, we have what's referred to as equilibrium. Every time a molecule jumps into the gas phase, a different molecule hops back into the liquid phase. And if we can measure that pressure of gas, that's referred to as the vapor pressure of that liquid. And that is temperature dependent. As we increase the temperature, okay, you can see this is just for different liquids, but as you increase temperature's on the x-axis here, the vapor pressure goes up. And when vapor pressure equals the atmospheric pressure, that's when a substance boils. Okay, so when the vapor pressure of a liquid equals the atmospheric pressure of the atmosphere, that is when things boil. Okay, so you can see ether boils at about 35 degrees Celsius, water is 100, mercury is 357 degrees Celsius. And that has to do with, as it turns out, intermolecular forces. Because when we boil something, we're breaking apart the intermolecular forces completely. Generally, that takes more energy than melting.